For our simple linear regression model, we assume that all of our data, all the x's and all the y's, are related to one another by this formula that you see over here. And this relationship is characterized by these constants that you see, the beta naughts, the beta 1s, and also this sigma square that you see over here. And then in the previous videos, we've considered estimators of beta naught and beta 1. And then we've actually never considered estimators for sigma square. So this is a constant that we know exists for our model, but how do we estimate this sigma square from the data that we have? So now in this video, I'm going to consider an estimator for sigma square, and the estimator that we're going to consider is this term over here. And then this expression is also known as the mean square error. And then in this video, I'm going to show you that the expected value of this estimator, which we call s square, is going to be equal to sigma square. And this is what I'm going to prove in this video. So in order to prove this, I'm going to find the expected value of s square. I'm going to drop this n-2 term. So for the rest of this video, I'm going to consider the sum of these terms that you see over here. So the terms wrapped around by the summation sign. So we have beta naught, beta 1 hat, and then xi squared. So in this video, I'm going to find the expected value of this expression. So in order to simplify this, I'm going to express beta naught hat by its definition. Beta naught hat is equal to the sample mean of y minus beta 1 hat times the sample mean of x. So I'm just going to substitute this expression inside this bracket. So I'm also going to drop the subscripts and the superscripts just to save myself some time. So you have minus beta naught, so that means you have a minus sample mean of y, and then plus beta 1 hat sample mean of x, and then minus beta 1 hat xi squared. And then I can group some of these terms together, which would help us develop some patterns. So we have yi minus the sample mean of y, and then we can pull out this beta 1 hat term, and then you can see that we have xi minus the sample mean of x. So for these two terms, we're just grouping them up by pulling out the beta 1 hat, and then we square this. So now next step, I'm going to square this entire term over here. So that for the expression wrapped around by the summation sign, we have yi minus the sample mean of y squared, and then minus 2 beta 1 hat yi minus the sample mean of y, xi minus the sample mean of y, xi minus the sample mean of x, and then we have plus beta 1 hat squared, xi minus the sample mean of x squared. So this is the expression that we have so far, and then you can see that obviously we can distribute this summation sign to each one of these three terms that you see over here. And by doing that, this is going to help us achieve some patterns which would help us further simplify this expression. So let us do just that. So first of all, we have the sum of all these yi minus sample mean terms, and then for this second term we have minus 2 beta 1 hat. So I'm going to pull this out because it's just a constant term, it's unrelated by the index. And then we have the sum of yi minus the sample mean of y, xi minus the sample mean of x. And then finally, I'm going to do the same thing, pulling out the beta 1 hat squared, and then we have the sum of all these xi minus sample mean of x squared terms. So you can see that we have three summation terms over here. And then we can actually combine two of these terms, because if you take a look at this term here in the middle, you will notice there is this particular expression. And if you go back to the first few videos where I was deriving the expression for beta 1 hat, I rearranged the expression for beta 1 hat so that it would look a bit more symmetrical, and I rearranged beta 1 hat so that it would look something like this. So if you don't remember this formula, you can check back on those videos, and I frequently use s_x as a shorthand for this expression just to save myself some time. The point is that you see this term here in the numerator. This is the exact same thing as this term over here. So instead of writing this summation term explicitly, I can actually rewrite it as, so this summation term, so yi minus sample mean of y, xi minus sample mean of x, is actually equal to s_x times beta 1 hat. And then for this expression over here, you can see that this term here is actually s double x. So this is the same as the expression for which I use s double x as a shorthand. So you see that this is actually just s double x, and then this term over here I just showed you is equal to s double x times beta 1 hat. So this term here is s double x times beta 1 hat. And so you can see that I can now combine some of these terms because you also have a beta 1 hat over here. So in the end, this entire term is going to be equal to negative 2 beta 1 hat squared times s double x. So let's just write this out. So now after all that simplification, we see that this term here in the middle, this is just minus 2 beta 1 hat squared. So don't forget that we have 2 beta 1 hat terms, and then we also have a s double x. And then here we also have a plus beta 1 hat squared s double x. And you can see that we can now combine these two, so in the end we just have minus 1 of these terms. So let's just get rid of this. So now we only have minus 1 of these beta 1 hat squared times s double x. So now this is the expression that we want to evaluate. And now I'm going to move the expected value sign to the inside of the summation sign. So instead of the expected value of the summation, I'll have the sum of the expectations of yi minus sample mean of y squared. And then for this other term, we have s double x. I can just pull this out. They're all non-random terms, and then I can move the expected value sign into the beta 1 hat squared. So now we need to evaluate this expression. Now if you want to evaluate the expected value of a random variable square, one way to do this is to understand this as the variance of x plus the expected value of x squared. And this is how we're going to evaluate these two terms. So you can see that this is the square of the random variable yi minus the sample mean of y. So this is just equal to the sum of the variance of yi minus the sample mean of y, and then plus the expected value of yi minus sample mean of y, and then squared. So we have this first term over here corresponding to this first term, and then for the second term we do the same thing. So we have s double x, and the beta 1 hat square, this is just going to be equal to the variance of beta 1 hat plus the expected value of beta 1 hat, and then the square of this entire expected value. So now we need to evaluate these two terms. So now let's deal with these two terms separately. So let's focus on this term first. So what is the variance of beta 1 hat? So we found what the variance of beta 1 hat is from one of the previous videos. So the variance of beta 1 hat is just equal to sigma squared divided by s double x. So you can check back on the previous videos if you don't remember this. And then the expected value of beta 1 hat, that's just equal to beta 1, because beta 1, as we found out in one of our previous videos, this is an unbiased estimator. So expected value of beta 1 hat, that's just equal to beta 1. So we've essentially dealt with this term over here. Now let's focus on this term. So first of all, we have this variance of yi minus the sample mean of y. So let's evaluate this first. Now for the variance of yi minus the sample mean of y, now we can evaluate this term by writing out the sample mean of y explicitly. That's just equal to 1 over n times the sum of all the y terms. So rearranging this, we have negative 1 over n y1 minus 1 over n y2, and this keeps on going until you reach the ith term, which is slightly different. We have 1 minus 1 over n for the coefficient of the ith term, and then it goes back to 1 over n for all the subsequent coefficients. And then the same pattern continues all the way to the end. So finally you reach the nth term, so we have minus 1 over n yn. And then in order to evaluate the variance of this term, this is just a linear combination of y terms. So I've used this same formula several times in the past few videos. If you're evaluating a linear combination of these y terms, if you want to find the variance, what you do is just that you take the coefficient and then you square it, so you have 1 over n squared, and then you multiply this with the variance of the y term, the random variable. And for this case, the variance of y1, that's just equal to sigma squared. And the same goes for the subsequent terms. So we have plus 1 over n squared, variance of y2, that's just sigma squared. And then this keeps on going until you reach the ith term, which is slightly different. You just have a different coefficient, and then you multiply this with the variance of yi, which is also sigma squared, and then all the rest of the terms have a coefficient of 1 over n squared until you reach the very end. And so you have plus 1 over n squared, so this should also be a plus because all the terms are positive, and then 1 over n squared, and the variance of yn, so sigma squared. So you can see that of all our n terms over here, there is one single term that behaves in such a way, and all the remaining n minus 1 terms, they're all equal to sigma squared divided by n squared. So we have n minus 1 copies of these sigma squared divided by n squared, and then we have this 1 over n squared sigma squared. So now we can combine these two terms. I'm just going to pull out the sigma squared and the n squared. And so we have n minus 1 plus, so I'm just going to rearrange this term in such a way. So instead of 1 minus 1 over n, I have n minus 1 divided by n. So now I'm pulling out the n squared. So the remaining term on the inside is just n minus 1 whole squared. And combining these two terms, we have n minus 1 plus n squared minus 2n plus 1. You see these cancel out. This also cancels out. We have negative n. So we have n squared minus n divided by n squared, so I can take away one of the n's. And so in the end, we have sigma squared divided by n times n minus 1. And so what this means is that, going back to this expression, this term over here, this is just equal to what we just obtained. So this is equal to n minus 1 divided by n sigma squared. And now we shift our focus to this term, so now we need to find the expected value of yi minus the sample mean of y. Now for the expected value of yi minus the sample mean of y, I'm just going to break this apart into the expected value of yi minus the expected value of the sample mean of y. So the expected value of yi, that's just equal to beta naught plus beta 1 xi. And then for the expected value of the sample mean of y, this is just equal to 1 over n times the sum of all the y terms. So I'm going to use the subscript j this time because this is just a subscript for the sum, so it's kind of different from this I. So I'm just going to use j for the subscript. And then we need to evaluate this expected value, and then we can just move the expected value sign inside the bracket. So we just have 1 over n times the expected value of all the y terms. So what this means is that finally what we now get is minus 1 over n times the sum of all these expected values. So the expected value of yj, that's just equal to beta naught plus beta 1 xj. And so now what we have is we have a beta naught plus beta 1 xi, and then now we have 1 over n, and then we have a sum of n copies of these beta naught terms. So we have n times beta naught. And then we have this beta 1, I can just pull this out, and then we have the sum of all these x terms. So the sum of all x terms, that's just equal to n times the sample mean of x. And so you can see that we have n times beta naught divided by n. So these two terms, they cancel out. And then here we also have an n, which also cancels out with the n in the denominator. So in the end, we just have beta 1 times xi minus the sample mean of x. And so this is another result that we've just obtained, and that's going to be equal to this term. And now we're ready to evaluate the expression that we have. So we're considering the sum of the variance of yi minus the sample mean of y, which we found to be equal to n minus 1 divided by n sigma squared, and then we also had plus the expected value of yi minus the sample mean of y whole squared, and then we found that for this term on the inside, this is just equal to beta 1 times xi minus the sample mean of x, and then we square the whole thing. So this is the sum of this entire term, and then we also have minus s double x times the variance of beta 1 hat, and then which we found to be equal to sigma squared divided by s double x. We found this in the previous video. And then we also have the expected value of beta 1 hat squared, and we found this is an unbiased estimator, so this is just beta 1, so that's just equal to beta 1 squared after you square it. So now we can evaluate the sum. So first of all, we have n copies of these n minus 1 divided by n terms, so it's just n times this term, so we just have n minus 1 times sigma squared. And then for this second term over here, I'm just going to pull out the beta 1 squared, and we have the sum of xi minus the sample mean of x whole squared. Now this term, that's just equal to s double x. So remember, s double x is the shorthand I use for this expression. And here we have minus s double x times this expression. So it just cancels out with the denominator, so we just have sigma squared. And then here we also have beta 1 squared times s double x. So here we have beta 1 squared times s double x. We have minus beta 1 squared s double x. So these nicely cancel out. And then we also have a minus sigma squared. So in the end, we have n minus 2 sigma squared. And this basically concludes our proof. So what we're looking for, what we just calculated, was the expected value of this sum over here. So we just found that the expected value of this sum, after all our painstaking effort, is equal to n minus 2 times sigma squared. So now, of course, if you divide this by n minus 2, you can see that the expected value of s squared is just equal to n minus 2 times sigma squared divided by n minus 2, which is, of course, equal to sigma squared. So you see that s squared is indeed an unbiased estimator of the term sigma squared.